Imagine you have an identical twin. You share the same DNA, the same birthday, and you've grown up celebrating every milestone together. Now picture this. On your 20th birthday, your twin, let's call her Stella, decides to become an astronaut. She's been given a once-in-a-lifetime mission to travel to a distant star system in a super-fast futuristic spaceship. You, on the other hand, decide to stay right here on Earth. Let's call you Terra. You wave goodbye, promising to keep in touch, and watch as Stella's rocket blasts off into the inky blackness of space, accelerating to an incredible speed, something very close to the speed of light. It's a bittersweet moment, but you're proud of her adventurous spirit. You go about your life on Earth. You go to university, get a job, maybe start a family. You watch the seasons change, year after year. The world evolves, technology advances, and you grow older, just as everyone does. You mark each passing birthday on the calendar, wondering what Stella is doing out there among the stars. From your perspective, her journey is set to take 40 Earth years. She will travel 20 years out and 20 years back. So, you expect to see her again when you are 60 years old. You've lived a full life, with all the ups and downs that come with 4 decades of human experience. You're ready to welcome your twin sister home. But here is where things get truly weird. And I mean wonderfully, mind-bendingly weird. When Stella's spaceship finally lands back on Earth, the hatch opens and she steps out. You rush to greet her, but you stop in your tracks. While you are now a 60-year-old with grey hair and wrinkles, Stella looks like she has barely aged a day. In fact, for her, only a few years have passed. She is still a young woman in her 20s. This isn't a magic trick or some kind of science fiction gimmick. This is a real predicted outcome of Albert Einstein's groundbreaking theories. This is the famous twin paradox, and it reveals a fundamental truth about the universe. Time is not the same for everyone. So how on Earth, or off it, does this happen? To get our heads around this, we need to travel back in time ourselves, to 1905. This was the year a young patent clerk named Albert Einstein published his theory of special relativity. It was a complete game changer, and it rested on 2 very simple but powerful ideas. First, the laws of physics are the same for everyone, as long as they are not accelerating. Second, the speed of light in a vacuum is constant. It doesn't matter if you're standing still or racing in a spaceship. You will always measure the speed of light to be the same incredible number, about 300,000 kilometers per second. This second idea about the constant speed of light has some seriously strange consequences. Think about it. Speed is just distance divided by time. If the speed of light is always the same for everyone, then something else has to change to make the maths work. That something else is distance and time. Einstein realized that for the speed of light to remain constant for a moving observer, their measurement of time must slow down, and their measurement of distance in the direction of motion must shrink, relative to a stationary observer. This isn't just a trick of perception. It's a real physical effect. The faster you move through space, the slower you move through time. This effect is called time dilation. It's a bit like when you're walking on a moving walkway at an airport. Your speed relative to the ground is your walking speed plus the walkway's speed. But with light, it's different. If you are on a spaceship traveling at half the speed of light and you turn on a torch, you don't see the light beam shoot away at 1.5 times the speed of light. No, you still measure it moving away from you at the normal speed of light. And someone watching you from Earth also sees that same beam of light moving at the normal speed of light. For this to be true for both of you, your clock must be ticking slower than the clock on Earth. Now, at the speeds we experience in our everyday lives, this effect is absolutely minuscule. But as you approach the speed of light, like our astronaut twin Stella does, the effect becomes dramatic. This is where people often get stuck. They ask, hang on a minute. From Stella's point of view in the spaceship, isn't it the Earth that's moving away from her at high speed? So shouldn't she see the clocks on Earth slowing down? Shouldn't Terra be the younger one when they meet? This is a brilliant question, and it gets right to the core of why this is called a paradox. It seems like the situation should be perfectly symmetrical. If all motion is relative, then who is to say who was really moving? The solution to this puzzle lies in a single crucial detail that breaks the symmetry: acceleration. Einstein's theory of special relativity, which describes time dilation due to high speed, only applies to observers moving at a constant velocity, that is, in a straight line without changing speed. But Stella, the traveling twin, does not have such a simple journey. To get to the distant star, she has to blast off from Earth, which involves a massive acceleration. Then to come back, she must slow down, turn her spaceship around, and accelerate all over again for the trip home. Finally, she has to decelerate to land safely back on Earth. This acceleration is the key. Stella feels forces that Terra, staying comfortably on Earth, does not. Terra remains in what physicists call a single inertial frame of reference for the whole duration, ignoring the minor effects of Earth's rotation and orbit. Stella, however, switches frames. She is in one inertial frame on the way out, and a completely different one on the way back. The act of turning around, the acceleration, is an absolute, undeniable event. Stella would feel the G-forces pushing her into her seat. She knows, without a doubt, that she is the one who has undergone the tumultuous journey. Because of this acceleration, the situation is no longer symmetrical. We can no longer say that, from Stella's perspective, the Earth simply moved away and came back. Stella is the one who has traveled out and returned, and it's this change in motion that makes all the difference. Let's break down the journey step by step. As Stella's spaceship accelerates away from Earth and settles into its cruising speed, something fascinating happens from Terra's perspective on the ground. Terra points her super telescope at her sister's ship and watches the clock on board. Due to the effects of time dilation we've discussed, she sees Stella's clock ticking much more slowly than her own. For every year that passes for Terra, she might only see a few months tick by for Stella. Terra watches her sister moving in what appears to be slow motion. It's a direct, observable consequence of Stella's immense speed. But what does Stella see when she looks back at Earth? According to the principle of relativity, from her constant velocity frame of reference, the Earth is the object that is moving. Therefore, when she looks back at Terra through her own telescope, she also sees the clocks on Earth ticking more slowly than her own. This is the part that creates the paradox. Both twins see the other's time as being slowed down. It seems impossible. How can both be right? It feels like a logical contradiction, but in the strange world of relativity, it's perfectly consistent during this phase of the journey. This reciprocal observation continues for the entire outbound trip. Let's say the journey to the distant star takes 20 years in Earth time. From Terra's viewpoint, she ages 20 years, but she calculates that due to time dilation, Stella has only aged, for example, 2 years. From Stella's viewpoint, she has aged 2 years, and she observes that the Earth clock has been running slow. She calculates that less than 2 years should have passed for Terra. So far, the symmetry holds. Each twin sees the other as aging more slowly, and there's no clear answer as to who will be older in the end. It's a cosmic standoff. The key to remember here is that they are far apart. They can't just meet up and compare watches. Their conclusions about each other's time are based on calculations and observations made from a distance. The signals carrying the information, the light from their clocks, also play a role in what they see, an effect known as the relativistic Doppler effect, which further complicates the visual picture. But the fundamental physical effect is time dilation. During this long, straight cruise through space, the paradox is in full swing. The tiebreaker, the event that will decide who is truly younger, has not happened yet. It's all building up to the most important part of the journey. Everything changes at the halfway point. After 20 years of Earth time, Stella reaches her destination. But to come home, she can't just keep going. She has to stop, turn her massive spaceship around, and accelerate back towards Earth. This, is not a gentle three-point turn. It's a period of immense deceleration, and then immense acceleration in the opposite direction. This turnaround is the single most important event in the entire story. It is the physical action that shatters the symmetry between the two twins and resolves the paradox once and for all. It's the moment the universe decides whose clock is right. From a physics standpoint, this is where Stella switches her inertial frame of reference. On the way out, she was in a frame moving away from Earth. Now she's about to enter a new frame, one that is moving towards Earth. During this period of acceleration, Einstein's general relativity, his theory of gravity and acceleration, comes into play. General relativity tells us that acceleration is equivalent to gravity. and strong gravitational fields can also cause time to slow down. The intense forces Stella experiences during her maneuver have a powerful effect on her perception of time elsewhere in the universe. As Stella is turning around, something dramatic happens to her view of time on Earth. The simple reciprocal time dilation she observed on the outbound journey is gone. During her acceleration, the now for Stella rapidly sweeps forward across the Earth's frame of reference. In a very short period of her own time, the days or weeks it takes her to turn the ship around, she would see the clocks on Earth jump forward by many, many years. All those years that Terra was living through on Earth essentially catch up in Stella's frame of reference during this brief, violent turnaround. It's a massive, rapid shift in her space-time perspective. So while Stella is fighting the G-forces and wrestling her ship into a new trajectory, she would see the feed from Earth's clock spin wildly forward. She left a 20-year-old Terra, calculated that only a couple of years had passed for her, but during this turn, she witnesses decades of Earth time flash by. Suddenly, she sees that Terra is no longer a young woman, but has aged significantly. This is not just a visual trick, it's a fundamental consequence of changing her motion through space-time. The acceleration forces a resynchronization of her now with Earth's, and in doing so, it reveals the massive time difference that has been accumulating. With the turnaround complete, Stella is now hurtling back towards Earth at the same incredible speed. The paradox might seem to reappear. Once she's at a constant velocity again, she is back in an inertial frame of reference. Looking at Earth, she will once again observe Terra's clock to be ticking more slowly than her own. And likewise, Terra, watching the approaching spaceship, will see Stella's clock ticking slowly. The symmetry of special relativity seems to be back in place, but the damage, so to speak, has already been done. The great age gap was locked in during the turnaround. During this 20-year return trip, as measured by Earth's clocks, the situation is much like the outbound leg, just in reverse. Both twins see the other's time passing more slowly. Terra on Earth ages another 20 years, bringing her total time past to 40 years. She watches Stella's clock and calculates that her twin has only aged another 2 years on the return journey. From Terra's perspective, Stella's total trip time should be about 4 years, 2 years out, and 2 years back. She prepares to meet her sister, who should now be a 24-year-old. From Stella's perspective inside the spaceship, her own clock tells her that 2 years have passed on her journey home. During this time, she once again sees Earth's clocks running slow. However, she can't forget what she witnessed during the turnaround. She saw time on Earth leap forward by decades. So even though she sees Terra's clock running slow now, she knows that a huge amount of time has already passed for her Earthbound sister. Her initial calculation that Terra would be younger is now completely out the window. She knows she is returning to a future she did not experience. The journey home is therefore a journey towards a known discrepancy. The puzzle is no longer a puzzle for Stella. She has the evidence of her own experience, the G-forces of the turn, and the rapid jump forward of Earth's timeline. She knows she is the one who has taken the detour through space-time, the one who has effectively jumped into the future. As she prepares for landing, she knows she is not returning to the world she left. She is about to meet a sister who has lived a full life in the time it took her to make a round trip to the stars. The reunion is set to be a profound and shocking confirmation of Einstein's physics. The moment of truth arrives. Stella's spaceship slices through the atmosphere and lands gently at the same spaceport it departed from 4 decades earlier. The world she returns to is familiar, yet different. The trees are taller, the buildings have changed, and the technology is more advanced. But the biggest change awaits her as the hatch opens. Standing there on the tarmac is an older woman with grey hair, and the kind of wisdom that only comes with age. It's her twin, Terra, now 60 years old. As Stella, still a spry 24-year-old, steps out, the reality of the situation hits them both. They stand there for a moment, a living, breathing paradox. One twin has lived through 40 years of history, while the other has experienced only 4. Terra has memories of raising a family, of a long career, of watching the world change decade by decade. Stella's last clear memory of Earth is from her 20th birthday party. For her, that was just a few years ago. The age gap is not an illusion. It is a physical, biological fact. Stella is physiologically 36 years younger than her identical twin sister. The time dilation predicted by Einstein is no longer a theoretical concept, it's written on their faces. This outcome definitively resolves the paradox. The question of who was really moving has a clear answer: the one who accelerated. Stella's journey, with its blast-off, turnaround, and landing, broke the symmetry. Her path through space-time was different. Think of it like two people traveling from Sydney to London. One person flies directly, taking the shortest route. The other decides to fly via Tokyo, then Moscow, then Cairo. When they both arrive in London, is it a surprise that the second person's odometer shows they've traveled a much greater distance? Of course not. In the world of relativity, space and time are intertwined into a single fabric called space-time. All objects are constantly traveling through space-time. When you are sitting still, you are traveling mostly through the time dimension. When you move very fast through the space dimensions, you have to trade some of your travel through the time dimension to compensate. Stella, by traveling a long path through space, took a shortcut through time. Terra, by staying put, took the long way through time, but a very short path through space. The reunion proves that the path taken through space-time determines the time elapsed. This all sounds like fantastic science fiction, but is there any actual proof that this happens? The answer is a resounding yes. While we don't have spaceships that can travel close to the speed of light, yet, we have performed incredibly precise experiments that confirm time dilation is a real, measurable phenomenon. We don't need to send a twin into space. We just need very, very accurate clocks. And we have them, atomic clocks, which are so precise they would only lose or gain a second over hundreds of millions of years. One of the most famous tests was the Hafele-Keating experiment, conducted back in 1971. Physicists Joseph Hafele and Richard Keating flew several atomic clocks on commercial airliners around the world, once eastward and once westward. They then compared the time on these traveling clocks with a reference clock that had remained stationary on the ground at the United States Naval Observatory. The planes were, of course, traveling much slower than Stella's spaceship, so the effect was tiny. But it was there, just as Einstein's theories predicted. When the planes returned, the clocks that had flown around the world were slightly out of sync with the clock on the ground. The traveling clocks had ticked ever so slightly slower, losing a few billionths of a second. The experiment had to account for both special relativity due to the speed of the planes, and general relativity due to the planes flying higher in Earth's weaker gravitational field, which actually speeds time up a bit. When all the calculations were done, the measured time difference matched the predictions of relativity almost perfectly. It was a stunning confirmation. The twin paradox is not a paradox. It's a fact of our universe. Another everyday proof comes from something many of us use daily, the Global Positioning System, or GPS. The GPS network relies on a constellation of satellites orbiting the Earth at high speed. These satellites have extremely precise atomic clocks on board. For your phone or car's GPS to pinpoint your location accurately, it needs to synchronize perfectly with these satellite clocks. But the satellites are moving fast, about 14,000 kilometers per hour, and are in a weaker gravitational field. Both effects alter the rate at which their clocks tick relative to clocks on the ground. If engineers didn't correct for these relativistic effects, GPS navigation would fail spectacularly, accumulating errors of about 10 kilometers every single day. So, why should we care about a seemingly absurd story about twins and spaceships? It's because the twin paradox isn't just a quirky thought experiment. It forces us to confront the true nature of time itself. It shatters our intuitive, everyday notion of time as a universal, absolute river that flows at the same rate for everyone. Instead, it reveals that time is personal. Your experience of time is unique to you and your journey through the universe. Time is relative, flexible, and woven together with the fabric of space. This is a profound shift in our understanding of reality. This idea has practical implications that have already shaped our modern world. As we've seen, the GPS in your phone only works because scientists and engineers understand and apply Einstein's theories of relativity every single second. Without correcting for time dilation, your GPS would guide you into a lake instead of to the coffee shop. The technology that powers so much of our navigation, logistics, and communication relies on the very principles that create the twin paradox. So, in a very real sense, you are using the solution to the paradox every time you look up directions. Looking to the future, as we dream of interstellar travel and exploring distant galaxies, the twin paradox becomes even more relevant. If we ever build spacecraft capable of traveling at significant fractions of the speed of light, time dilation will be a major factor for the astronauts on board. A trip to a nearby star and back might take decades or centuries for those on Earth, but only a few years for the crew. These explorers would effectively be time travelers, jumping into Earth's distant future. Planning for such missions requires a deep understanding of these effects, not just for navigation, but for the human and societal consequences. Ultimately, the twin paradox is a beautiful illustration of the power of scientific curiosity. It starts with a simple question, what if? And leads us to a deeper, more wondrous view of the cosmos. It teaches us that the universe is often stranger and more magnificent than our common sense can imagine. It reminds us that even the most fundamental concepts like time can hold surprising secrets. So the next time you look up at the stars, remember Stella and Terra. Remember that out there time itself can bend, and a journey through space is also a journey through time. And that's not just science fiction, that's science fact.